we'll have the final lecture by Aninda Sinha.
Right, okay. So this is lecture 3 of entanglement entropy in holography. And the idea in this lecture is to tell you about the Liu-Takanagi conjecture for calculating entanglement entropy in holography. I'll also tell you about some generalizations of this to higher derivative theories. And originally I thought that maybe I can talk about the proof of this proposal using an argument due to Liukovic and Madasena, but I think I won't have time to cover that. If you want to talk to me about that, I'm happy to talk to you separately about it. So, but the other thing that I wanted to cover is tell you something about how to calculate relative entropy in holography. So just let me remind you of a few things, relative entropy. And so in the last lecture, I told you to remember two things. One of them is something called strong subadditivity. Strong subadditivity, the inequality looked like S of BC plus S of AB is bigger than S of or equal to S of ABC plus S of B. So I'm going to show you how to prove this in holography. And the other thing that I talked about in the last lecture was relative entropy between two states, rho and sigma, and I proved for you that this is positive. So I'll also tell you how to check this in holography. So, but before I begin, did you have any questions for me related to what I said in the last lecture? Okay. So let's begin. So in the last lecture, towards the end, we saw that, or we reviewed how black hole entropy is calculated, and I told you that black hole entropy can be thought of as a minimal surface, and there's some entropy functional whose equations of you work out the surface equations from that entropy functional, and it gives you the black hole entropy. And the Liu-Takanagi conjecture is partly motivated by this. And the conjecture is that you have your field theory that is living on the boundary of ADS. So this is the boundary of ADS. This is the bulk. And you want to calculate the entanglement entropy of this region. Then the conjecture states that you have to find a surface that is extending into the bulk of ADS. You have to find the surface that is extending into the bulk of ADS and ends on this boundary. So the entanglement entropy for this region A is the minimal area of this surface, let's call this surface sigma, ending on the boundary, and divided by 4G. So this is the proposal, and so let me show you an example. So how do you find this minimal area? This minimal area is found by minimizing an entropy functional. This entropy functional that I'm writing down is for Einstein gravity, entropy functional for Einstein gravity. And I wanted to talk about, for example, for concreteness, I wanted to talk about 4D and 4D boundary and 5D bulk. This surface is a codimension 2 surface because we will set t equals to 0. So that's why, and then there is an equation that tells you how it is extending into the bulk. So there's another condition. So this is condition 1. There is another condition. So it's a codimension 2 surface. So the entropy functional is an integral over 3 volume of the square root of the determinant of the pullback metric on this surface. There's some normalization of 2 pi over LP cube. So let's work out a concrete example. Let me work out in detail this example that will be of relevance to the second part of my talk as a spherical entangling surface. So what you do is you start off with the bulk metric, ds square. I'll be in Euclidean signature, but then since I'm going to put t equal to 0, it does not matter. So this is your 5-dimensional ADS. This is the metric for the 5-dimensional ADS in Poincaré coordinates. Now we put t equals to 0 and rho is some function of the radial coordinate f of z. Then this pullback metric becomes L square over z square dz square 1 plus f prime square plus square. So this is your pullback metric. So this implies that square root of h is 1 over z cubed 1 plus f prime square to the half times f square. So you're supposed to, this is your Lagrangian for f, and you're supposed to work out the equations of motion for f. Equations of motion for f from this Lagrangian, from that Lagrangian, and in this particular case, there's an exact solution. You can just go to Mathematica, work out, ask it. You can easily work out the equation of motion by hand as well, but you can easily check on Mathematica that this particular function f of z is square root of some constant r square minus z square is an exact solution to this equation, whatever follows from there. So this r is nothing but the radius of the spherical entangling surface on the boundary. That's because z equal to 0 is the boundary. So f of 0 is r, and this is the radius of the S2, the spherical entangling surface. So after you work this out, you go back to this entropy functional that I've written there, S, and you plug this into the functional and carry out the integral. So S is going to be 2 pi over L p cubed, and the integral is going to be over d theta d phi and dz. So it's sine theta d theta phi dz times something. Now you can carry out the integral exactly, but then that is not going to be of relevance to us. What we are going to focus on, so remember that I told you that this entanglement entropy in field theory had an expansion, so the leading order looked like some area law divided by some cutoff, in this particular case epsilon squared, and then plus there were subleading terms, and there was a particularly interesting subleading term that came with a log. The log of r times epsilon times some number and dot dot dot. According to the rules of ADS-CFT, z equals to epsilon, or z being small corresponds to the ultraviolet cutoff that appears in that formula. So that's all that we're going to do. We are going to plug in that on-shell expression and expand the integrand around z equal to epsilon. So that's also easy to do. So what you're going to find is that this works out to be some number times r square over epsilon square, then minus 4 pi square L cubed over Lp cubed, yes, and log r over epsilon, dot 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 dot. And this is exactly of the form that I've written there.
That's the only solution that's regular. So
Very good question. So by regular you mean that whether it closes or smooths?
yeah. So that's about the condition at the zero radius.
Yeah. So this is the only solution. You can explicitly check that. So what he's asking is that the picture that I've drawn here, it's the surface that is closing off smoothly at some point in the interior. Okay, is that always guaranteed that you're going to find something like that, or do you find more solutions where maybe the surface does not close, it just goes to infinity? And you can check that in this particular case, you can assume that it closes off at some radius, leave it unspecified, raise it to some power alpha, unknown power alpha, and you plug it in, you'll get an initial equation for alpha, and you'll find that only alpha equal to half is a solution, which corresponds to this particular case. But it's a very important question. I'll tell you why when I discuss higher derivative stuff. Yes. So that is one example where you can work things out completely explicitly, including the expression for the surface everywhere. Another example of sorry. This is a Lagrangian, so I should use a different. So that L is that guy, and this capital L is this radius that appears here. There is no 1 over epsilon, it's only even powers. Yeah. No constant term either. So if you wanted to get a constant term, instead of having a spherical entangling surface, you can do it for a strip, for a slab, and then you'll get a constant term. So the other, yeah. So for the rectangular strip or the slab, actually you don't get any log terms. You just get some divergent terms and a constant.
How can you tell that's scheme dependent where you have a constant or not?
This one? Well,
you rescale epsilon and you will get a constant.
Yeah, actually you're right. If I rescale epsilon, I will get some log of lambda. That's true.
So you cherry picked epsilon.
Yeah, I should correct myself. Thank you. Yes. So what he was saying is that I could easily rescale epsilon, and then I'll get some 4 pi square L cubed over LP cubed log lambda, where lambda is a scale dependent factor. So yeah. Yes, thank you. Okay, so here you found an exact solution, but the fact that you find an exact solution is not guaranteed. But as you can see, in order to get an expansion of that form, you don't really need to know the solution everywhere. You can try and do a Pfefferman-Graham type expansion for the surface itself. And that's exactly what happens in the second example, which is that of a cylindrical entangling surface. So this was for a sphere. For the cylinder, the bulk metric looks like this. Again, you play the same game. You put t equal to 0. R is some function of z. You work out the Lagrangian. In this particular case, you get something very similar to that, except that this power of f will not be square, but it will be just linear. So you simply get z cubed 1 plus f prime square times f. And you can go and work out the equations of motion, and then you will find that, well, what you're going to find is the current way of concluding that an exact solution does not exist. You go to Mathematica, you ask it to find an exact solution, does not produce any output, and you conclude that an exact solution does not exist. But then, but probably if you were clever enough and you did it differently, you might be able to find an exact solution, but one does not exist easily in this case. What you can instead do is you can expand. So you want the radius of the cylinder to be r. So the leading order term has to be a constant around z equal to 0. So that's the radius of the cylinder, r. And then you can perform a series expansion. You can do it systematically, and what you'll find is that the leading order correction is at order z squared. Add z to the power 4, you will get something like this. This coefficient you won't be able to determine using this analysis. This is typically what happens in the Graham expansion as well. It breaks down at order z to the power d. There is also a log term that appears. This coefficient you can determine. It's minus 1 over 32 r cubed z to the power 4 log z and dot dot dot. Well, it turns out that if you were just interested to carry out this expansion up to the log term, then the log term that appears in this surface solution does not play a role. It's only the first two terms that play a role. So in fact, even F4 does not affect that result.
I'm sorry, what's the difference now compared with the first example?
So this was for a sphere. So sphere. So this was I presented the flat boundary in spherical polar coordinates.
Right.
So boundary was dt square plus d rho square plus rho square d theta square plus rho square sine square theta d phi square. And here I've written it in cylindrical coordinates. Yeah, it's a cylinder, so dw is the length of the cylinder. W is integrated over. So in the entropy functional, the integral is over. It's a codimension 2 object. So the integral here was over dz, d theta and d phi. Similarly for here it will be over dz, d theta and dw. So dw does not appear in the Lagrangian. It's the range of integral. You put some cutoff, so it's minus h to h. That's going to show up in the answer. So then you repeat this exercise, and what you'll find is that this looks like some number times r times h. H is the length of the cylinder divided by epsilon squared minus 2 pi l cubed h. H is again the length of the cylinder divided by lp cubed over the radius times log r over epsilon. So again, even in this particular case, it's of that form. Now, as I said in my previous lecture, that the coefficients of the logs are to be there's some relation with the conformal anomalies, and so let me just tell you that there is an independent argument that can be using an independent argument. You can actually show that this conformal, the Euler anomaly A, and this guy for the cylinder is the other. The one associated with the Weil square C. Okay, so for a cylinder you get C. For a sphere, the leading order answer is A.
So sorry, I guess my question was, you're describing the same space with different coordinates.
Yeah, but the entangling surface is different. So the entangling surface in the boundary, in one case for the sphere, right? So okay, let's go through this.
Okay, the way you divide the regions of entanglement is different.
So yes, so here, if I put rho equal to capital R, and so that is what is happening to the entangling surface on the boundary. The entangling surface on the boundary is simply capital R square d theta square plus R square sine square theta d phi square. So that's a sphere S2 of radius of capital R. So similarly for the other. Any other questions? Okay. So in order to find the entanglement entropy, we are minimizing some area functional, and just using that, we can easily prove. Can give a proof for strong subadditivity, and the proof is as follows. So for strong subadditivity, you require 3 intervals. So let's consider 3 intervals A, B, and C. And I'm just drawing it on a line, but then it's difficult to draw the diagrams completely for this particular case. But just imagine that these are the 3 intervals. So I want to find. So this is some section of the boundary. And on the left hand side of that inequality, it is SBC plus SAB. So SAB is given by the on-shell minimal action for this surface. SBC, this guy, is given by this. And on the right hand side of the inequality, you have again SABC. SABC is this surface, and SB is just this surface. So now, why is this, if the inequality was correct, this has to be bigger than that? How do you see that? The argument is very easy. So all that you notice is that you can just deform this shape a little bit here and think about this to be equal to this. Okay. But so by dissolving the surfaces here, I've created a new surface which joins up, which will correspond to something that is for the interval ABC. But the true minimal surface, the true minimal area is actually this surface. So in this picture, the area of this surface is bigger than the area of this guy. Similarly, this one is not the true minimal area. The true minimal area for SB is this. So each of these quantities, whatever is outside and whatever is inside, is bigger than the relevant the corresponding quantities here. So trivially, you have this must be greater than or equal to SABC plus SB. Okay, so that's a one-line proof of the strong solidity.
Is there any requirement for the shape of surface to be convex?
Yeah. So your question is whether it's
That
closing
one
off.
is not. Right? Have to resolve the outer one.
Right. The outer one is so this is not the true. So what I was saying is that we started off, the left hand side was equal to this configuration.
Yes.
Okay. Now you can think of I can draw the picture a little bit differently, where I remove that point and I look at it this way.
Yes.
So I've got a surface that is joining up like that, and then I've got another surface that is joining up like that. But this is not the minimal area corresponding to ABC, and so this is greater than this the area corresponding to this surface, and similarly this is also greater than the area corresponding to this surface. Yeah. You are probably asking a slightly different question. So you are asking, why does it close off smoothly in the bulk? If that's a question, then I'll address it in a bit. Any other questions? Yes.
Do you need ADS to prove such kind of property?
This proposal, this view taxonomy proposal, can be checked concretely only in area spacetimes.
Strong subjectivity is always true, right? With this strong subjectivity is always
Yeah, strong subjectivity is always true. This statement is supposed to be true in quantum mechanics.
Oh,
But
so
he's
No,
asking about
I'm saying it's true in any geometry. Say if you want to define the function.
if it
like
comes
this.
from a minimal area, yes. It just requires, so if you postulate that your entanglement entropy, what you want to identify as the entanglement entropy, comes from some minimal area, so you have some entropy function and you're minimizing that, then of course this follows. Because in the argument, in the diagrammatic proof, all that I needed for the argument is that this is there's some minimal area, so the true entanglement entropy is given by some other surface. So yeah, so if there's a minimal area, then it will just follow. Yeah.
So the solution that you find here actually is just an extrema surface. How do you?
It's a well, I would call it a minimal surface. Extremal surface is reserved for time-dependent cases.
Yeah, but here actually you are just solving the
Sure, yeah.
Euler Lagrange
Yes,
equation,
yes.
which come from
Sure, you're
condition
estimating,
for
but then
extrema,
it's
right?
also minimal surface, yeah, minimal area, yeah.
Is it always guaranteed that it is a minimal surface? How do you know that?
Yeah, that is a good question. In this particular case, I guess you would consider fluctuations and then see what is happening to the fluctuations. Yeah. So you have to check. You have to definitely check it. I agree with your point that you have to check it that actually it's a minimal area, not just an extremal area. That's exactly what happens in time-dependent diagrams because you have some. Because it is an extremal surface and not really a minimal surface, you can't prove the strong separativity easily. Okay. So let me tell you some comments about what happens in high derivative gravity. So let me write down a general four derivative action. So my five dimensional gravity action, bulk action. Let's write that as and now you want to ask whether there is a corresponding area functional for this theory. And your first guess would be that, well, for black holes we know that there is a Wald formula to compute black hole entropy. So maybe we do something similar. We just say that. So in the black hole calculation, what you do is you calculate the derivative of this action with respect to the Riemann tensor, and then you contract it with the binormals. So this A, B, epsilon, C, D, these are binormals. So I told you that this is a codimension 2 surface, so there are two normals. So each of them are just an antisymmetry combination of the two guys. So this is how you would go about calculating black hole entropy for Killing horizons, bifurcate Killing horizons using this formula. And you would have thought that let's try and do something similar. So what I'll do is I'll take this action, I'll work this out, whatever comes out from this, and that is my area function. That would be a first guess. But this works out to be wrong. The check that you carry out to show that this is wrong is that you take that particular area functional and you work out the universal term in the spherical, for the spherical entangling surface, you get the right answer. You work out the universal term in the cylindrical entangling surface. Instead of getting C, you'll end up getting A. Okay, so that's what would happen if you just use this formula. Now, in the Wald entropy functional, actually, if you go and look back at the literature, the entropy functional proposed by Wald needed to fix certain ambiguities in the theory, and it turns out that the way that you fix the ambiguities works fine if the extrinsic curvature for the surface on which you're computing the entropy vanishes. And this is not true. The extrinsic curvature for the cylindrical entangling surface actually does not vanish. So whereas that's why it gives you the right result for the spherical entangling surface, but it does not give you the right result for the cylindrical case. So is there any other proposal? And